Hi everyone, in this presentation we will mainly talk about how to improve the area detection ability of Hamming code and some applications of Hamming code. The whole presentation will be divided into 4 parts. The first 2 parts is about the method that could improve the Hamming code, and the third part is about the application of Hamming code. The last part is about the area correction code for dynamic random access memory cache.
Okay, now let's start. My topic is improved Hamming code. So firstly, I will introduce the traditional Hamming code for you. Then I will indicate the problems of the traditional Hamming code. And then I will introduce the improved version. Firstly, let's see the constraint of the Hamming code. 2 power p should larger or equal to m plus p plus 1. And here, p is the number of parity, m is the data size, 2 power p is the number of states, and 1 means all correct state. And why the formula looks like this? Firstly, parity bits are the redundant bits, which is not used to store the data. Parity is only used for detecting the error. Error can happen in any bits, including the parity bits. So the number of bits that the error can happen is m plus p, like this. And p is parity bits have totally 2 power p states. If we want to use parity to detect errors happen in each bit, the number of states should be larger than the total number of m plus p. Also, there is one more state to represent all correct state. That is to say 2 power p should larger or equal to m plus p plus 1. Now let's see an example. Here, let's assume that the transmitted data is this. And for Hamming code, it looks like this. Here, P are parity bits. They are located at 2 power n. And Hamming code actually groups source data into different groups according to the weights. And now let's see how the Hamming code groups them. As you can see, the yellow parts show different groups. Take the first parity as the example. 1, 3, 5, 7, 9, 11 are in the group 1. And for 2, 3, 6, 7, 10, 11 in the group 2, etc. By observing their binary code, you will see the least significant bit is 1 in group 1. And for the second group, the second least significant bit is also 1. For the third one, in the same manner. So now that we have already know which data are in the same group, we can get the parity bit. And we use exclusive OR to get parity bit. For example, this one in group 1 we have 1, 3, 5, 7, 9, 11. So in 1 we have P, in 3 we have 0 and 1, 0, 1, 0. And once we use exclusive OR, we will get 0 for the first parity bit. And in the same manner, we can get P2, P3, and P4. Now we will get the complete Hamming code. And suppose here the received data has some error in the 9th position. And we calculate the parity bit in the received Hamming code, which is this one. And we will find that the red area actually violates the even parity checking. So it means the value of 1001 indicates that position where the error happened. 1001 is exactly 9, so it means 9 has error. However, there are some problems in all the traditional methods. Firstly, let's see why it's so magic. Because those parity bits p are weights of the binary, which is in the position of 2 power n. Once one position has error, the index of that position will reflect in weights by the violation of even parity. Those even parity errors in index can help us find the real error index again. Now that we know base of Hamming code is using weights, the larger the index is, the more weights bits will be used. In other words, the smaller index is, the less number of bits in the process of Hamming bits calculation. Therefore, this can improve the efficiency. Based on this analysis, I propose a new improved Hamming code. Now also let's see the constraint. The constraint of the improved version is 2 power p minus 1 should larger or equal to m plus 1. And here m is the data size, and p is the number of parity bits. Also, I will explain why the formula looks like this. So why m plus 1? Because the errors can only happen at any position of the data, and 1 means the all correct state, and y 2 power p minus 1. Also, those errors can also happen at any parity bits. Therefore, we need one more bit to check the error of parity bits. That's why we mean minus 1 here, so that the p minus 1 bits can represent all data index, and 1 bit is used to check the error in parity bits. Actually, the improved version is quite straightforward, and the idea is to put all the parity bits on the left side and the data on the right side. And here I will analyze a new version based on the example, and here is the transmitted data, and here is the actual Hamming code. And how to group them in the improved version. Similar to the traditional version, the improved version also uses weights to represent each index. The only difference is that the improved version places all the weights on the left side so that the number of index can be as smaller as possible. It means 127 used to store all the data, and the index can be as small as possible. In addition, this approach can also reduce the number of weights. So 8, 9, 10 is enough to represent 127, because 3 bits is enough to represent 8 numbers. And the aim of 11 is to distinguish the data and the parity bits. When the position 11 is 1, it means parity bits. When it's 0, it means data. The reason that the 8, 9, 10 can only represent 2 power 3, which is 8 states. And to represent the state after 8, we should use one more state to represent those parity bits, which is 11. And for the advantage of the improved version is to reduce the number of bits in process of Hamming bits calculation, because as you can see here we only use 4, 5, 5, 5, and totally it's 19. And for the old version, we need to use totally 20 bits in the calculation. And I will give you more details in the following slides. And now that we have already know the data in each group, we can get the parity bit based on the exclusive OR in the same manner as the old version. So for P1 we have 1, P2 is 0, P3 is 0, P4 is also 1. And now let's see how arrow checking works. Here let's suppose the received data is 10010, 100010, and here the arrow happen in the 5th position. By calculating the parity bits, we can get 0101, and the red areas means those the position violates even parity checking. So 0101, which is 5 in decimal, means the position 5 has error. Now let's discuss the advantages of the improved version. So mainly, let's compare the number of bits in the process of Hamming bits calculation. For the traditional version, we have 4 plus 4 plus 6 plus 6, which is 20. For the improved version, it's 4 plus 5 plus 5 plus 5. It's 19. Even so, it seems that there is no significant improvement because we only reduce 1 bit here. However, once you increase the data size, you will see the significant improvement because once the data size is so large, the index of the data, it will always be so large. And for the traditional version, those index will be much more larger than the improved version, because in the improved version we put all the data index on the right side. We try to minimize the range of the data index. However, in the traditional versions, the data index will be so large, and we will use more ways to represent all of the data index. That's why it will consume more bits, and eventually it will reduce the efficiency. That's all. Thank you.
After listening to the last method, which put all the ways together, let's take a different way of thinking. Generally, there are 3 common error detection codes. There are parity check, Hamming code, and cyclic redundance check. For the parity check, it can only detect odd digit area in the data, and it cannot locate or correct those areas. And for the Hamming code, it has high area correction ability for single bit area, but not for multi-bit areas. For the cyclic redundance check, it can detect and correct multi-bit area in stored information, but its implement is very difficult and expensive. Therefore, all the method has its own advantage and disadvantage, so if we can combine them together according to those characteristics, it may have a wonderful effective. Therefore, a simple and effective way to improve Hamming code is to combine Hamming code and parity check. On the base of Hamming code, parity check is used for information bit and redundant bit, and most of the multi-bit area can be detected after correcting 1 bit area. Assuming that the information bit is 8-bit, so the redundant of the Hamming check are B1, B2, B3, and B4. Then we're using the parity check for both information bit and the redundant bit of Hamming code. We can get the parity code odd. Then we should send this information to the receiver, and in those information, it could include information bits, Hamming code, and parity check. When decoding this message, we need to take out the redundant bits to get S1, S2, S3, S4, and then calculate the order check. The result is shown in this picture. When the order check is 0, and S1, S2, S3 is both 0, it means there is no area. And when the order check is 1, and the S1, S2, S0 is not all 0, so there is one bit area. When all check is 0 and S1, S2, S3, S4 is not all 0, it may have multiple bit area or one odd area according to the odd correction. Therefore, this improved Hamming code can detect most of the multi-bit area and can reduce the misdetection rate.
Well, now I want to talk about the application of Hamming code in video watermarking. Watermarking is a kind of mark that help people to protect their ownership for their pictures or videos. And then I want to introduce you about the watermarking. The digital watermarking technology has made a very big progress in recent years. The direction is still focused on the image and audio watermarking technology. So I have an idea that to improve the video watermarking scheme just based on the Hamming code technology. Because the Hamming code can effectively improve the recoverability, robustness of the watermarking. Okay, now I want to talk about the principle of using the Hamming code. Hamming code is a type of error correction scheme, and the coding error can be corrected by Hamming code. So Hamming code is often used in memory, but we still can use Hamming code in watermarking. A code word with n equal m plus r is the basic idea, and then R correction factors generated by R supervisory relations are used to distinguish the error free from n bit of error at different positions in the code word. And the R in M, they have the relationship just like 2R must equal or bigger than n plus 1, or the 2R must equal or bigger than m plus r plus 1. Okay, let me introduce you how to use the Hamming code in watermark. Well, the first step is that error correction information is generated by watermark information W according to the error correction code algorithm G, and the video data D can be separated into brightness information Y and chroma information. The chroma information is usually UV, CRCB, IQ, this kind of type. And the third step is to use the algorithms just like E1, E2, E3, whatever you want. You can add many algorithms to improve the robustness of the watermarking. But you just want to make it easy, you just need to make them just like the same algorithm. If the more algorithms, the more robustness of the watermarking, but it's harder, and the process of the embedding watermark is more. So whatever you just need to do whatever you want in this step. As the fourth step is to combine the brightness information I mentioned in step 2, and in this information need to be embedded with the watermark information and the chroma information embedded with the error correction information into the video data D, and you can get the new video data after embedding the watermark. Okay, after embedding, we still need the extraction. Watermark extraction process. The first step is to embed it. Is that embedded video data need to be separated into the brightness information Y and the chroma information. The same step, just like the before, like the embedding step, the second step, and the extraction process step 2 is to use the algorithms D1, D2, D3. You use how many algorithms you use in the embedding process. You need to use the same number of algorithms in this step to extract the watermark information W and the error correction information R1, R2 from the brightness information and chroma information respectively, and D1, D2, D3 correspond to E1, E2, and E3 when embedded respectively. And the different algorithm can enhance the robustness, just like what I said before. And the third step is that W, R1, and R2 can restore the watermark W according to the error correction algorithms C. Okay, this is all the process, the embedding process and the extraction process. Now I want to talk about the significance of this application of Hamming code. Hamming code can obviously improve the robustness of the watermarking, and it shows that the embedded domain also makes full use of the available space of the video information. This scheme does not require complete decoding, so it really reduces the complexity of computation and improves the real-time performance. Okay, so I think Hamming code is really useful in embedding the watermarking in the video. Okay, that's all my presentation. Thank you.
Hello everybody. Our topic is beta error corrective code, and my part is an error corrective coding method for DRAM machine. This method is used in embedded hardware design, storage, energy saving design field. So it is really important for nowadays our architecture of computer, because we want to save our storage, save our energy. If there is some error here in the architecture, when the computer works longer and longer, it would cost more energy and more efficient to work. So let's start. First is the background of DRAM error collection. Large DRAM interconnection result in increased refresh power consumption. Embedded DRAM cache is highly integrated and needed to be refreshed frequently. 3. DRAM energy consumption increases as the DRAM capacity increases. 4. Smart refresh technology by adding a timer to each row to refresh and skip the most recently visited row, which can save more memory cells and save energy. The content of our error correcting coding method is in order to improve the refresh cycle, reduce the refresh frequency, and ultimately reduce power consumption. An error correction coding method for DRAM cache is provided. Technical solution to solve the problem is first solution is increase the refresh cycle of the DRAM cache and reduce the refresh frequency. Second is encode and decode the data in the cache. Encode and decode the data in the cache. The first part is encoding. The data in the buffer is encoded using BCH code. The input data D is K bits, and the input data D is multiplied by the matrix G to obtain a data encoding information U, so that the data is stored in the encoding and the R bit check bit is added. B. Decoding. Judging the type of error based on the coded symptom S, and using error correction methods based on the type of error. In decoding, the first step is if S is 0, there is no error in the data. If which digit in S is non-zero, then the digit is an error. 2. The second part of decoding is if there is only one bit error, use a single bit error correction method. Third, if the error has more than 2 digits, use the multi-bit error correction method. Here is the equation for the decoding method. In 1-bit error correction, S is equal to V multiplied by H squared of T is equal to quote U plus E quote multiply H square root T, and the U plus E is equal to D multiply J plus E multiply HT is equal to E multiply HT. Input data D is K base, and the input data D is multiplied by the matrix G to obtain a data encoding information for you, so that the data is stored in encoding and the R digit check is added. In the next equation, E is the number of bits of error information, and V represents the coded information with error E. Then 2-bit error correction. Find the number of error bits in S first, then determine the error location and correct the location error. Suppose the number S bit is 1. First look for the number of error bits in S, then determine the location of the error and correct it. Assume that the S number is 1. Si is equal to A square ji multiplied by I plus a square j2 multiplied by I plus until aj multiply I. Sigma x is equal to 1 plus sigma 1 x plus until sigma t x t squared, and is equal to 1 minus a squared j1 multiplied by x, 1 minus j2 multiplied x, until 1 minus aj t multiplied by x. In the equation, j represents the error bit check and t represents the error check bit. The position for the error bit is overturned and the corresponding misalignment is corrected. The decoding of this uses two error corrections. The number of H row is t multiply m plus 1. T represents the maximum number of errors, and m represents the length of the data way. The error correction method for this is 5EC6ED. The advantage of the error correction method. This is the final of my part. This would reduce the number of memory cell refreshes, and also the refresh cycle is long and easy to lose. The multiple bit error correction coding ensures that the data is correct. Also, the multi-bit error correction function is powerful. Compared with the traditional method, the cost is low and the space is small. That's why this method is really useful for our architecture. Okay, that's all.